解锁，请启出话筒。
Okay, let's start. Good morning to everyone. Let's do some recap and then I'll take some question. I'll answer some question from you guys. Okay, so let's do some recap on Legendre symbol. Okay, so we learned a few ways to compute this. Okay, to decide whether a number is a quadratic residue. Okay, so let P, Q be odd prime, and then P doesn't divide AB. There's one thing I want you to note here is if P doesn't divide AB, right, this actually implies that the GCD of A with P or the GCD of B with P is 1. Okay, because P is prime. Okay, so you can only have a common divisor either 1 or P. Okay, if it's not P, then it is not divisible by. Okay, so the condition of relatively prime with P means that the prime cannot divide that number. Okay, these two are equivalent. This is not true for any P, but for prime it's true. Okay, because P, you only have 1 or P as well. Okay, so there's a two-way direction here. Okay, so these two conditions are actually equivalent. Okay. Divisible by P and the GCD equals 1 with P. Okay, so first thing is the Euler's criterion. Okay, so Euler's criterion tells you that this number here, you can compute congruence to A to the P minus 1 over 2 mod. Okay, but something to note here is here it says congruence not equal. Okay, but we could deduce or equal. Okay, because this value here always be plus or minus 1 mod P. Okay, this is what we proven last time. Okay, and this Legendre symbol only takes plus minus 1. Okay, obviously it's congruent to plus minus 1 mod. Okay. Okay, so number 2. So congruence is not that good. But then we have Gauss lemma. Okay, Gauss lemma could compute this number immediately. So Gauss lemma says that you just take minus 1 to the power s. But what's this s here? Okay, so this s is to count some set of number. So this set of number is some number that's greater than P over 2, obviously depending on your prime. such that this set of number is picking from a multiple of a, okay, up to p minus 1 over 2a. Okay, right. And then we told you how to decide whether minus 1 is a quadratic residue, okay, if and only if p is congruent to 1 mod 4. And we also told you how to decide whether 2 is a quadratic residue, okay, if only if this is congruent to plus minus 1 mod 8. Or there's a formula for this, is minus 1 to the p square minus 1 over 8. Okay, you should imagine that this formula is coming from yeah, coming from either Euler's criterion or Gauss lemma. And there's some property of the Legendre symbol. Okay. So for example, if two numbers are congruent to each other, then their Legendre symbol is the same. Or if you can split up your numerator into products, then you can also split out your Legendre symbol into products. And from here, we can deduce that if your number is a perfect square, then the Legendre symbol is always 1. And lastly is the law of quadratic reciprocity. Okay, so this will tell you that if I just swap the numerator and the denominator, what happened to the Legendre symbol? Okay, so these two are related by minus 1 to e minus 1 over 2 times q minus 1 over 2. So if you look at the right hand side, the formula doesn't matter whether you put p or q, because you can just. Okay, so over the weekend, right? Sihan, I'm not sure I understand your problem right or not. Are you asking that why 1 is always a quadratic residue or any square? You mean this one? Any square? Yeah, you so basically you're asking why this is true. Is it? Yeah, so why is this true? So basically I said this comes from here, right? So you could write like a square p equals to a over p times a over p, right? Okay. So a over p could be 1, 1 or minus 1, minus 1. So both of them have to square to 1. Right? Because okay, so maybe if you don't know this, then I need to remind you what is a over p. So this only has two choices, right? Either plus 1 or minus 1. Okay, so if a is a quadratic residue of p, then it is plus 1. Then if it is not, then it is minus 1. Okay? Yeah. But then I can ask a question. Why 1? So I mean last time we said that 1 because equals to 1 square, then it is 1. But then can you see why 1 is always a quadratic residue, or can you always find a solution to x squared equals to 1? Congruence 1 mod 2. Sorry? Okay. Sure. I mean prime have a primitive root, but then x squared congruence to 1 mod p is very special. You need the inverse to be itself. I don't know. We know that inverse exists, but why inverse have to be itself? Or can you straight away find me like the solution that solve x squared congruent to 1 mod? Can you quickly find a solution to this? Huh? 1? 1 Oh, one is always true, huh? You are right. Good. One is always true. Hmm. Yeah, one is always true. Good. Yeah, one. So you can actually take x congruence to 1 mod p. Or I thought of the other answer. You can take p minus 1 also. Yeah, because if you p minus 1 square, what do you get? P square minus 2p plus 1. So congruence to 1 mod p. Okay. Uh, yeah. Sorry? P plus 1 square also works. Yeah, but p plus 1 is just 1, right? Yeah. Okay. So you can see that. You see? 1 and minus 1. I think that's it. Right. So do you have more questions? Last time you asked me that. Do you still have questions? Not this chapter. Uh, is there a lot or just a few? A lot. Okay. You haven't sent me also. You didn't send me yet. Okay. Oh, okay, sure. Yeah. Right. Yeah. Any other question? I mean, do you have question for this chapter? Maybe you can do first. No? Okay. Yeah. Yeah. Any question? Any other question? Good. I haven't finished marking your assignment yet. Hopefully, I can return you by tomorrow. Uh, Another thing is, I think we have holidays on Friday. You guys heard of it yet? Don't know. No. I think it's just announced yesterday. So maybe we need another replacement class. Yeah, so you're gonna have Friday, Saturday, Sunday, and Monday for holiday. Yeah. I'm not sure the school is announcing soon or not. If that happens, shall we book a time for next Thursday? Okay. I want to see majority. How about Thursday morning? Thursday morning. Can raise up your hand if you can do Thursday morning. Thursday morning. Can you do higher? Morning. Okay. Thursday afternoon. I think morning have more people. Okay. Maybe we will go on the same time. Okay, Tuesday morning. But if you can't make to replacement due to other class, that's fine. You no need to inform me. Okay. I will check back with you again. Okay. Yeah. Most probably we will have holiday. There's an extra holiday. Okay, for Hari Raya. It's just announced yesterday by the Prime Minister. So let's see how it goes. Okay. To start, maybe to do some warm up. How about try this question? Okay, try and compute this. Use whatever method that we have done. I give you 3 minutes. Okay, let's try. Okay, so 713 is not a prime, so I cannot just use law of quadratic reciprocity. But you realize that it can be split into 23 and 31. Okay. Is it what you do? Sorry, nothing wrong. Huh? 1000. Okay, thank you. 1000. Okay. 1000. Ah, shit. I copy wrong. Okay. So, yeah. So what should I do here? Mm, is this possible? How about I go back and compute this and then see what you get? Uh, I didn't see the 9. Can this be computed? I think. Okay, shall we do this? In that case, we do this. Let's see how it goes. I also never compute this. Actually, I wanted to do the lecture notes one, but then I have a solution already. You can have a look. How about we do this? We just do this together. Okay, let's do this together. Okay. Well, is this possible? Okay, let me see. You don't have quadratic reciprocity to help you. Is this possible? Cannot sub point and bottom. Is there any way to simplify this? I think. I think no tool is useful for this unless you just solve it directly. Hmm. Anyone got idea this one? Or you stop here? Hmm. 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 Have to be prime. Let me see. Let's check. Let's check. So do we have to start with prime? Okay, I think we are good. Right. So P have to be odd prime. Okay, so this question doesn't work actually. So we have to start with odd prime. I think because otherwise you don't have the inverse property, right? Then it's very hard for you to solve. Yeah. Okay, so we have to stick with 1009. Yeah, let's start with this one. Okay. So what we can do here is we split everything into primes already. Then we can use quadratic reciprocity to sort top and bottom. Okay. So P have to be prime. So when you read the question, please take notes. P have to be all prime. Maybe I highlight this. Okay. So from here, is it okay? Because what do we need to check here? we need to check whether 1009 is congruent to what mod 4. Is it 3 mod 4? 1 mod 4? And then 23, 3 mod 4? And then 31, also 3 mod 4. Okay, so what's this thing here? Well, I guess we have to state another corollary here, which is this one. Not here. Okay, so maybe a more useful form of law of coordinate reciprocity is this. Well, you can remember that formula to help you to deduce, but then you can remember this slide here. Okay. So you can just swap it as long as you have 1 mod 4 appears in either top or bottom. If both of them is 3 mod 4, then you have to have a -1. You can deduce from the formula just now, but then this one is already computed for you. Okay. So in this case here, you have a 1 mod 4, okay, in one of the spot. So you just swap it. There's no minus sign. Okay, and then you can simplify some more. Okay, take 1009 mod 23, and then take 1009 mod 70. I'm sorry, 31. Okay. Okay. Then you can further split. Okay, further split your Legendre symbol into 2 squared times 4. Sorry, times 5. And then for the 17, you can swap again because they are 2 odd prime. Okay. So this swap here, we note that one of them is also 1 mod 4. Okay, so there's no sign occurred here. And 17 and 31 are odd prime. Okay. So the first term you get you 1. The second term, what I will do is I'll do quadratic reciprocity again. And the last one you simplify further. Okay. And then second term, why can you swap? Because we got the 5 mod 1 actually. So there's no sign occur here. Then you simplify again, so become 3, 5. And then the other one you split into 2, 17, and 7, 17. That. And then 3, 5 is not 2, not -1, so you cannot decide. Or you can straight away solve it. If not, you quadratic reciprocity again. Okay. Can you straight away solve it? Is there anything square to 3? Is there anything square to 3? I mean, there are 4 choices, right? 1, 2, 3, 4. Anything square to 3 or no? Okay. 1, 1, 2, 2, 4, and then 3, 3, 9, 4, 4, 16. Okay, nothing square to 3. Okay, either you can straight away compute this is -1, or you can do quadratic reciprocity again. Yeah, solve again. Okay, so if you swap, then you will look something like this. And then 2 over 17. This is checked against mod 8, right? Yeah, okay, so 17 is 1 mod 8. Okay, so it's a +1 here, right? And then 7 over 17, what do you do? We will use quadratic reciprocity again. So here you notice that one of them is 1 mod 4, so there's no sign change here. So if you use quadratic reciprocity on 3, 5, you also note that one of them is 1 mod 4. Okay, so there's no sign change. Here you get 10, 3, actually 3, right? 3 over 7. Okay. So 3 over 7 here also you can solve similarly. You can straight away solve it. Just check 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, mod 7, you get 3. Actually, you do, right? You do? Do you? Do you? Do you get mod 3? Huh? Cannot? Cannot? Let me see. Is it true? Uh, yeah. You can't? Kind of weird. Oh, no wonder. Then my solution got problem. Okay, I think you can't. Okay, good. Okay, so let's say okay, so let's say we can, right? So let's see we use a law of quadratic reciprocity, see what we get. So 2, 3 is 3 mod 4, sorry, mod 8. Okay, so here you should get a -1, right? Okay. But then what is 3, 7 here? Okay, so 3, 7 here, let's say we're gonna use a law of reciprocity again. So, but then 7 is congruent to 3 mod 4, right? And then 3 is congruent to 3 mod 4. Okay, so there's a minus here. So you have a -1 times 7 over 3. Okay, so altogether you get 4 over 3. Okay, which is 2 square 2 over 3, which is 12. Okay. Any questions so far? So far, any question? Any questions so far? No? No? Okay. Okay, if no question, so basically it is whatever we learned before. Okay, so deciding whether 2 minus 1 is a quadratic residue, and then use law of reciprocity, and then yeah, basically that's it. Okay, so these are very handful too because if you can swap top and bottom, definitely you can make the smaller number go to the bottom, and then you use the modulo property here. Okay, so make your number even smaller and smaller until you can check by hand. If not check by hand, then check using number 2 or -1. Okay. Okay. So next, we're gonna introduce some notation called the floor. Okay. Looking like this. Okay. So this is a bracket that only have a bottom, or at the top is open. Okay. But then in your textbook, I think they write like this. Okay, this is the textbook notation. So the textbook just write a bracket X. Because in reality, there's something called the what's the other name? The ceiling. Yeah. I'm gonna say the roof. Okay. So in reality, there's something called the ceiling. Yeah, the ceiling is like this. Sorry, like this. Okay, so here is the floor. So what's the floor here? Well, it's very intuitive. It's the largest integer that's less than or equals to x. For example, the floor of 3 is -3. The floor of -3 is -3. But then the floor of 1.25 is 1. Okay, it's not 0. Okay, it's the largest integer that's less than or equal. So it's like you remove the decimal. But then for -1.25, the floor of this is -2. Okay. So in your mind, you should have something called the number line here, right? So, and then you have an integer as your measure, right? If you look at your ruler. Okay. So if it's -1.25, right, it's somewhere here. Is it somewhere here? 1.25, sorry, should be here. Okay, -1.25. So it's the largest integer that's less than or equals to x. So you wouldn't pick -1 because -1 is already larger than this one -1. Okay, so you're gonna pick -2. Okay, similarly, if you go for 1.25, okay, you're gonna pick the largest integer less than or equals to x. Okay, you won't pick 2. Okay, does it make sense so far? Okay, so you need to have this number line in your mind, and you know what's going on. So this number line is exactly telling you this next sentence here. So the floor of x is equal to n if and only if x is in between n and n plus 1. Okay, so in this case here, -1.25 is in between -2 and -2 plus 1, which is -1. Okay, so you pick the left hand guy. Okay, you pick the left hand. And then obviously, if you take x minus the floor of x, it should be in between 0 and 1. Okay, so meaning this gap here is just at most 1. Okay, the gap here is at most 1. Okay, so the gap is at most 1. Does it make sense? Okay. Yeah, because if you go more than 1, right, then your largest integer will change already. The largest integer less than. Okay, if you go more than 1. If you jump out from this box, then your largest integer will change from like that. Does that make sense? Question? Any question? Any question? Okay, so if you go more than 1 from this box, then your largest integer will change. For example, if you stay at, let's say if you stay at any color that I haven't used, okay, -0.5, then your largest integer becomes minus. Largest integer that is less than or equal to. Okay, so other than this, we return to this division algorithm a bit. So that Q that you always find in your division algorithm, right? Actually, we can express it using this flow here. Okay, flow of A over N. Yeah, flow of A over N. Do you believe this? Maybe we can try some numbers. So let's say phi equals to 2 times 2 plus 1, right? Okay. So the claim here is this 2 here is equals to the flow of A over 2. Okay, but A over 2 is 2.5. Yeah. So this makes sense precisely because of this gap here. Okay, because of this gap here. Okay, because of this gap here. So in this case, the ruler here is no longer differ by 1. It's actually differ by this n that you divide. Okay, so it's differ by 2 by 2. So so maybe your ruler become this. Instead of differ by 1, then your ruler will differ by this. Minus 4. And then where is 5? So your 5 is here. Okay, and then your plus 1 is this part. Does it make sense? Yeah, so the largest integer is still the largest one. Largest integer. Yeah. So if you think of this scenario here, right? So this remainder here would be divided by 2. So your remainder there's like 1 and 0 and 1. 0 and 1. Okay. Got question? Any question? Okay. So you can think of this division algorithm as a different ruler based on what you divide by. Previously, you can think of it as divide by 1. There's nothing in the denominator. You are like x over 1, right? X over 1. Okay, but then here is x over 2. Okay. So if you add your remainder more than 2, then your ruler will jump. Okay. Right. Okay. So this is not very important, but the more important thing is about this formula here. So we're gonna introduce another way to compute the Legendre symbol. Okay. So P have to be odd prime, like what we counted just now. And then A here is an odd integer not divisible by P. Has to be odd, not divisible by P. Then you can use another counting here called the P of AP. Okay, P of AP. So what's T of AP here? So this is the reason why we introduce this notation before, because we're gonna sum this flow together. Okay, so what's this flow doing here? So maybe let's write down what is it. Well, again, you sum from 1 to p minus 1 over 2. So in this chapter, you have seen a lot of p minus 1 over 2 appearing already. So this is kind of a magic number in this chapter here. You don't sum everything up. P minus 1 over 2 is enough. Okay. And then you look at this flow here. So what's this flow here? Well, you multiply your j with a and then divide by p and then take the flow. So the first term you will get is a over p, the flow of a over p. The second term will be 2a over p, and then all the way up to p minus 1 over 2 times a over p, and then take in the flow. Okay? Does it make sense? Okay. Okay. If that makes sense, maybe we can try one calculation, and then I'll let you try the other. So let's just compute the Legendre symbol of 7, 11, 7 over 11, and 11 over 7 using T7, 11 and T11, 7. Okay. So I'll do 7, 11 and then I'll let you try 11, 7. Okay. So to do that, we need to check what is T7, 11 first. Okay. So the formula is summing up from J equals 1 to P minus 1 over 2. So our P in this case is 11 minus 1 over 2 of the flow of JA over P. So our A here is 7, P here is 11. Okay, this is it. Well, what is 11 minus 1 over 2? It is 5. Okay, so you will sum the multiple up to 5. And like that. Okay. So so the first one is 0 point something, right? So the flow is 0. Second one is 14 over 11. So it's 1. The third one is 21 over 11. 1 as well. Okay, you haven't reached 2 yet. And then 28 over 11, 2. And then 35 over 11, 3. Or one way to quickly do it is like you can write it as in this form, right? 1 over 3 over 11. And then this one is 21 over 11, which is 1 and 10 over 11. And then this one is 28 over 11, which is 2 and 6 over 11. And then this one is 35 over 11, which is 3 and 2 over 11. Okay, so this is another way to see what the floor is. Okay, so in this case here, my previous lemma, 7 over 11 is minus 1 to the t of 7, 11, which is 7. So you get minus 1. Okay. Okay, so try and compute what is 7 t of 11, 7. Okay, everyone got the same? The same? Okay, good. Okay, so let's see. Wait, let's see. Actually, this lemma gonna use to prove quadratic reciprocity, but then we will just see it using example. Okay, we won't prove it, but we will just see it as an example. Yeah. So in your assignment, right? Some of you say you prove something, but you just show it for one example. It's not enough, because if it is a theorem, I mean, it's true for all numbers, right? You need to really prove for all numbers. You cannot show it for just one number. But to prove something wrong, you just need an example. Okay, to prove something that's true for all, you just need to provide a counterexample. Okay. So in this case here, we are not quite proving it, but just to give you evidence enough for you to believe, okay, that you can prove it. Actually, you can generalize this argument here. Now what time is it? 10:46. Because this proof is kind of long, can we speak half of it and then we come back again? Yeah, maybe we won't finish it, but then we will speak half of it and then we can come back after the break. Okay, so determine the number of lattice point that lies in the rectangle of 0 from x of 0 to 11/2, and then from 0 to 7/2 for y. And then split them by using this line here, y equals to 7/11, x. 7x/11. Okay. So let's do some part first. Okay. So let's note that. Okay, so the lattice points that we mentioned here are actually just referring to the pairs of integers. And so these pair of integers are just x, y such that they are both living in the integer. Okay, so meaning these points, these dot 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 point. Okay, so we just care about lattice point. Okay, so these are called lattice. So how many of them in this range here? Actually, there are 15 such pairs. 15 such pairs in the rectangle. But there's some very interesting observation here is no one will stay on the line exactly. Okay, no one will stay on the line exactly. So how do you check this? Do you know how to check this? No one will stay on this line. Okay, stay on this line here. So basically, if it stay on the line, meaning it solve the congruence. I mean, solve the equation. So meaning you have to prove that none of these lattice points will solve this equation. So you can do analysis like this. So because if 11x equals to 7y, this will implies that 11 will divide 7y. Okay, but then what does this mean? 11 is a prime. Okay, so either 11 will divide 7 or 11 will divide y. Okay, 11 divide 7 is impossible. Okay, but can 11 divide y or not? Where is y? Your y is just 0 up to 7/2. Okay, it's a number that's smaller than 11. So both of them cannot happen. Okay. Yeah. So both cases cannot happen because 7 less than 11, and as well y is just in between 0 and 7. Okay. Yeah, strictly. So yeah. 什么 ex 对 cx 等一下，为什么 why this is true? You asking this? Okay, because this line is y equals to 7/11x. I do opposite. So should I swap? Yeah, I should. Okay, let's swap it. So here is 7y times 7x. Okay, let's see if our arguments work again. So because 11 will divide, sorry, because 11y equal to 7x, this implies that 11 should divide 7x. So either 11 divide 7 or 11 divide x. So what's our x? Our x is in between 0 and 11 over 2. Still less than 11. Is it okay? Okay. Yeah. Okay. Why I have this swap? Because your textbook is in the other direction. So I have to modify. Yeah. So sometimes I forget to change. Okay. Maybe we can stop here first and then we can continue later. Okay, let's break until 11:01. Yes. Yeah. 按
我直接这样看到它的屏，我就可以直接打击它。
这样确实是，可以，
对吧？
可以，因为那时候我们是想说把它抹掉先，可以，你要直接拆掉也是，诶，不是可以，下面也是这个，这个是这个，
对呀、
对，这个是有一个同学问吧，我记得，
嗯，
嗯，
我
也
们绕了一下。
还没来，这样子结束也可以，这样结束也可以，都可以。嗯
这个定义它说 x 偏方 a 的话，它是在1到22之间，所以就是某就是是需要 x 是1到22之间，还是就是全部？因为他有说用 table 这个嘛，它这个
哦，I mean，如果你 mod，如果答案是 mod 11的话，你也不能写完每一个出来吧，因为 应该 mod 10已经是把所有的可能性都写进去
因为我想他不是说用 a 嘛，然后 a 的这个有这个
这个
x，我觉得可以让 k 有范围，它就是为
嗯嗯嗯，因为我们有一个 theorem 是说，你如果找到这个 k 过后，然后这个 k mod 22都是它的答案嘛，对不对？嗯，所以你的答案确实是无限个，但是他这里只是叫你找一个给他，是吧？叫你找一个给他，就是
这个是解，
没有，这个他的意思是说叫你找完所有的可能性，对吗？
嗯，
呀。But then 你要知道的是，那个 theorem 告诉你说它会重复性嘛，23过后它就开始回来1了，24它就2，然后就重复性，所以再算它只叫你算20。这个的话要 for all，所以意思说你要有那个 mod 的答案在，这样你才会有所有的可能性。哎，明天上课？为什么？
就是能不能调整，因为第5周有课对吧？现在第4周也可以收，这样也会大家都来上。
因为也不会全部人来上课，其实下个周末， 只是说因为我们需要时间 book 那个课时，可能会 book 不到课时，如果明天了。
要是不一
对对对对
来不及了，
对对对对，
是周五的周第5周的周四。
对对，或者就这个走势。什么？你是不能来啊？你是早上下午都不能？
哦，我只能下午，我是
哦，你的下午了。
对我3、4、5分钟。就是问一下，能不能不周二上？因为周二我是可以的。
OK，因为来不及补，我也希望是把但因为昨天他宣布要太突然了，他是昨天宣布的。
我不知道。
哦，你们不知道哈，因为他是新闻出的，我不知道学校已经跟进了嘛。对
没事，我就是问。
呀，你可以搜一下，你可以搜一下，开在节什么补假额外假期就会出来。呀，你看一下。But then 明天是有点赶啊，除非这个拜四，But then 拜四也是吧？没有，不要补。什么新闻啊？开斋节啊，对，开斋节补假啊？什么？月亮早出来还是晚出来？没有，他就是说不用等月亮，他就直接补，就是额外多加一天啊，所以拜五到拜一都是假期。Yeah，他早又不要讲，I mean like 他要，I mean 他要看月亮他就看啊，I mean like but then 就放多一天吧。OK，take attendance，苏月、杰森、施杰森、范家豪陈宪、洪婷、蒋泽，OK，任波，Yeah，一航、陈一航，OK，思莹、韩思莹、韩思莹，Never seen her before，刘真贤，刘真贤，Yeah，Tiong Don Jun，叶伟通，陈子涵，子涵，陈子涵，陈子涵，王金珍，王金珍，王金珍，홍이 자， 홍이 자， 홍이 자， 对，陈子，OK，胡崇瑞，陈思曼，嘉诚，丁真，浩云，哦，OK，you come to front，OK，浩然，心怡，陈心怡，陈心怡，陈心怡，文琪，田文琪，田文琪，张小柔，张泽瑞，陈凯莹，Tiffany，Jacket，Yasin Jasmine，OK，嘉俊，嘉悦，泽新，韦明涛，OK，杨旭成，曾一飞，OK，陈玉清，李玲毅，李玲毅，应该说林毅，OK， 花园曹花园王雅浩聪李浩聪刘艺书潘子良甘金浩何明轩何明轩 OK 谭 OK you Saudi Ayub Joy Lee yes 明浩何明浩黄棋子秦子祥熊培成张馨予周瑞敏赖文义陈志陈子睿李小环曾天健Aaron Fabian Isaac 林科高硕喂 Isaac 林科高硕思涵思怡明先Okay, let's continue counting this lattice point here. So how does this 15 points tell us about quadratic residue here? Okay, so let's continue. So we divide this 15 pairs into two groups. So I mean, from this picture, obviously you would know what two groups is, right? One is above that line, y equals to 7 over 11x. The other one is below it. Okay, so let's see. Okay. Well, so how do we say above this line or below the line? So we will write it like this. We divide these 15 pairs into two groups. Okay, so first of all, let's fix our x-axis. So we'll fix our integer x. Just consider 1 up to 5 is enough, right? Because it's from 0 to 11 over 2. So the integer between these two numbers is 1, 2, 3, 4, 5. So actually there are 7 over 11 times x allowable value of y that satisfy 7x greater than 11. Okay, does this make sense? Okay, well, so let's put it back here. So let's go back here. So here is 11, y equals to 7x. Okay, so maybe I can ask the question. So where is 7x greater than 11y and where is 7, so the other way around, 11y greater than 7x? Okay, what do you think? Well, I mean, like we can change this, right? I mean, we can change it slightly. So this would implies that actually y is less than 7x over 11. And then the other one would implies that y is greater than 7x over 11. Correct, no? Okay. But then the middle line says what? If you are on this middle line here, this is exactly y equals to 7 over 11x. Okay. So from here, can you decide? So let me label that. So here is 1, here is 2. So 1 is above or below? Below, right? Okay, so because it says what? Your y value, okay, your value of y, okay, is less than this 7x over 11. But then this line is exactly those points that are 7 over 11x. Okay, does that make sense? Is it slightly confused here? Okay, if you are confusing, right, you need to ask yourself, what is this y here? This 2y is actually not the same. Okay, so you need to think of y is just some number that is 7 over 11x, which is on this line. Okay, so meaning if I put x, so let's say, okay, so maybe I show you some examples so you know what am I talking about. So let's say I take x equals to 1, okay, your y is 7 over 11, right? So this just says that if you look at x equals to 1 and then look at this line here, this point here is exactly 7 over 11, okay? But then if you look at the first inequality, right, it is something that's less than 7x over 11. So it's something below this line. And all the y's that below 7 over 11x. Okay, and then if you plug in different x's, right, these are all your 7 over 11x. Okay, so 1 is in this region here. And then 2 obviously is on the other region when your y is greater than this line here. Okay, if you like, I can rename the line to be like y1. Okay, so that your new y here, for the first one, it will be less than y1. It will be less than y1. And then the second one will be greater than y1. Okay, so that you just compare on the y direction for each x. Does it make sense? Okay, so in this case here, which one I wrote first? 7x greater than 11, right? So we are looking at the bottom region here. Okay, so how many possible points are here? So this is what we are counting here. Okay. So how many possible region? You can see that this depend on your 1, 2, 3, 4, 5, right? Okay, so you can see that when your x grow, the allowed point getting larger. But there is a way to compute this, There is a way to compute this. Okay, there is a way to compute this. Okay, maybe I show you. So if I put 2 here, what do you expect to get on this line here? It is 14 over 11x. Correct or not? Okay, so if you put 3 here, what do you get? 21 over 11x. And then if you put 4 here, what do you get? 28, 28 over 11x. Okay, and then all the way up to this 5 here. Okay, so this 5 here, what do you get? 35? 35 over 11x. Okay. Do you think this 5 number is very familiar? Is this what we have computed before? See? Okay. So what are you computing this floor? So this floor get translated into this chart here. Okay, so what do you get? Number 0, 1, 1, 2, 3, right? 0, 1, 1, 2, 3, I remember this. So if you see this lattice point, right, is it 0, 1, 1, 2, 3? Below this number. Okay, so actually we are counting this pair of integers here. Does that make sense? Okay, so the 0, 1, 1, 2, 3 represent how many pairs of integers such that satisfy this condition below the line 11y over equal to 7. Okay, so from here, so the total number of pairs satisfying 3 conditions. Okay, one is your condition on x, the other one is your condition on y, and then you have this line controlling you. Okay, so these are exactly the T7, 11. Okay, so this is exactly the T7, 11. Okay, let me finish it. Okay, so this is exactly the T7, 11. So what are these pairs here? Okay, so maybe let me write here. This is T711. So what are these pairs? Actually, we can list them down. So these 8 pairs are 2, 2. Sorry, 2, 1, 3, 1, 4, 1, 4, 2, and then 5, 1, 5, 2, and 5, 3. Okay. Okay. But then on the other hand, we can look for the other condition. On the other hand, check for 7x less than 11y. Okay, we change the other direction. And then using the same technique, we will see that there are 8 of them. There are 8 of them. So namely 1, 1, 1, 2, 2, 2, 3, 2, 1, 3, 2, 3, and then 3, 3, and then 4, 3. Okay, so this will give T11, 7. Okay, so if you don't believe, maybe you can go back to T11, 7 again. Okay, so it's 1, 3, 4, right? Okay, so if you go to this picture here, so where's your 1, 3, 4? So in this case here, we are looking in the horizontal direction. The 1 here, then 3 here, and 4 here. 1, 3. Yeah. Okay. Well, consequently, what we see that is actually, just now, did you notice why these two number occurs here? Okay, why these two numbers occurs here? Okay. So what you notice is, on one side, we can have 7 minus 1 over 2 times 11 minus 1 over 2. Okay, so what's this? This is like the power appearing on the quadratic law of reciprocity, right? Okay, so what's this number here is 3 times 5, which is 15. But on the other hand, if you take the okay, so if you take the T711 plus the T of 11.7, okay, this also will give you the same number. Okay, which on one of them you get 7, the other you get 8, right? Okay, you also get 7 plus 8. Okay, so hence we see that if you just use the quadratic reciprocity formula to compute, you also get the same thing by computing using this T711 plus T11.7. Yeah. Okay. Yeah. Okay. So why is this true? Because the previous lemma tells us that -1 to the T711 is just 7 over 11. Okay, and then on the other side, you get 11 over 7. Okay, so from here to here to here to here. Okay, yeah. So we have to prove, if you want to prove quadratic reciprocity, you need to prove that this two sum here always sum to this product. Then you will prove the quadratic reciprocity. Okay, so this part here is by the previous lemma. Okay. So to establish proof of law of quadratic reciprocity, need to prove the exponent. They need to prove that they have the same exponent. Okay, so on one side is a product, on the other side is a sum. Okay. Yeah, because these represent the lattice point, right? Correct or not? This represents the lattice point. But then here we split the lattice point into two parts. Okay. Surprisingly, after splitting into two parts, we can make one of the exponent become to calculate one of the Legendre signal. Okay, I think this lemma is very important. And because the top of that line and the bottom of that line compute different Legendre signal. Okay. Yeah. And so yeah, so this formula here that we mentioned in the quadratic reciprocity, right, really come from this counting here. So actually it comes from this sum first. And then we realize that this sum is just adding up all the lattice points. So if you want to add up all the lattice points, just count how many on the left, how many on the right. Because this lattice point come in a cube, right? Or a rectangle. Okay, so you just take how many on the width, how many on the length, and then multiply them together. Does that make sense? Okay, if it is not a rectangle, then you cannot have this formula. You just get something summed together. Because this is a rectangle, so you can write your formula in a product of like length times width height. Okay. Does it make sense? Okay, so next time if you see this formula, right? Quadratic law of reciprocity, law of quadratic reciprocity. This is really counting this lattice point here. Okay, so there are like p minus 1 over 2 on this side, and then there's like q minus 1 over 2 on the other side. Okay, and then half of it will compute half of the Legendre symbol. Let's say this part of it is TPQ, the other part of it is TQP, and then TQP will compute the other one. Does it make sense? Yeah, so this is the origin of this formula here. Because last time I didn't tell you how it came from, right? You just use it. But then it's come from counting this lattice point. Again, then if you want to ask deeper is why this lemma is true, then you need to look at the proof. Okay, I think we won't present this proof, kind of long. Okay, any question so far? Or at least you know where this formula comes from. But then if you want to ask further, then you need to go a bit further. Any question so far? No? Okay. Actually, there's a application of this law of quadratic reciprocity to find prime. So remember that I speak in the first class, right? Whatever we wanted to do now is like we try to check whether a given integer is a prime. Okay, so there's like a few tests you can do. Like from here in particular, we could, let me see, where is it? We could introduce some test called the tapping test. Okay, so this tapping test will be to test whether a Fermat's number is a prime or not. Okay, so this Fermat's number looks like this: 2 to the 2 to the m. Okay, So it's a prime if and only if 3 to the fm minus 1 over 2 congruent to 1 mod fn. Okay, so maybe you might think that this Fermat number is like very weird. Okay, actually it's not weird based on what you know on our prime numbers. For example, if you take m equals to 1, what do you see this number as? This number is 4. Okay, so if you take, sorry, so should I write like this? So m, what if m equals 0? If m is equal to 0, then f0 is 3. Okay, m equals to 1, f1 is 5. See, it's matching our first few prime. Okay. So m equals to 2 is, sorry, what someone said? 17, right? 17, yeah. Okay, so you see, this formula is kind of making sense, but then is it always a prime or not? So it turns out that it's not always is a prime. So at some point I think you will met that it is not a prime, but then if it's a prime, then the following things will be true. Okay. Yeah. So far, so good. Yeah. Yeah. So they are using quadratic reciprocity in some of the steps when you prove it. Yeah. So there's something that's not prime. So quite large, this non-prime number here. When you reach m equals to 5, your number is pretty big already. So I mean, like, they would like to give a formula to get primes. Okay, they would like to give a formula to get primes. But then I guess a lot of time they fail. Okay, so they have to prove why they fail or how to test whether it's a prime. Okay, because we prove that there's infinitely many primes, right? So I mean, like, for mathematician, right, we like to see pattern. Okay, we like to see pattern and then we would like to write down the pattern. But unfortunately, this prime number seems like there's no pattern. Okay, we try, you see, if you look at this Fermat's thing, right? So we kind of trying to give a formula to write down the prime, but then don't quite work. Okay, and then so if there's no pattern, so they ask for distribution. Okay, how does this prime number distribute? So maybe you can ask a question that is like in the first 100, right? There's how many prime? The second 100, there's how many prime? Third 100, there's how many prime? So or from one prime to one prime, what's the distance? Does it make sense? Yeah. So these are the questions that interest mathematician a lot. Okay, so it calls the distribution of prime. How does it distribute in our number line? Okay. Okay, if no question, maybe we could continue. So let's continue. So we'll go to a super version of Legendre symbol, which we call the Jacobi symbol. Jacobi symbol here. Okay. So again, let n be an odd positive integer with prime factorization. So in this case here, the denominator is n. There's no more prime, but then it's odd with prime factorization. And let a be an integer that's relatively prime to n. So meaning for all the pi appears here, right? It cannot appear in the prime factorization of a. So the Jacobi symbol of a over n will be defined as the product. Okay? So you just split it into the product of a over p I to the power pi. That's it. So let's say if an has GCD greater than 1, then we will just define it to be 0. Yeah. So it's the same case as the Legendre symbol. Again, we can define it to be 0 whenever n divide a. Yeah. Okay. So far it's like that. So what do you think? What kind of number this Jacobi symbol can get? What sort of number it can get? What do you think? Yeah, 1 or -1, right? Because it is just a product of Legendre symbol. Okay, you just get a bunch of 1 and -1 multiplied together. So you still get 1 or -1. And yeah, and then so far I think that's it. All good. All right. In that case, can you try and compute this? Compute this too, based on what we discussed just now. I give you maybe 2 minutes to try. Yeah. Okay, let's try. So what do you do? So you split it into prime factorization, right? Okay, so what's the prime factorization here? 3 square times 5. Okay, so meaning you need to compute 2 over 3 square times 2 over 5. Um, if you can, I think this is -1. Okay, otherwise you just equate to 1. And then the other one is, again, -1, right? Mod 8 is like -3 mod 8. As long as not plus -1 is -1. I mean, if as long as p is not plus -1 mod 8, then this number is -1. Then altogether you get a -1. Yeah. So this Jacobi symbol kind of solved the problem just now, right? Our Legendre symbol doesn't have doesn't okay. Our Legendre symbol need p to be prime, but then this Jacobi doesn't need p to be prime. Okay, but then I think later we will see. Can we see? What does this Jacobi symbol do? Yeah. Yeah. Wait, so what's this Jacobi symbol doing? Very interesting. Doesn't say here. Okay, I'll look it up for you. I think next class I will tell you what can this thing do. So far, it's just calculation in your notes. Okay, I will let you know what it can do next time. Okay. So, okay, next. How about 109 over 335, 385? Well, we can split it into 109 over 5, 109 over 7, and 109 over 11. Okay, and then you can further reduce 4 over 5, 4 over 7, and 10 over 11. Then you can see that, oh, two of them are squared, so 1 times 1. The other one is, luckily, is just minus 1 over 11, so you can use your criteria to check. So this is 3 mod 4, which is minus 1 here. Let's get my. Okay, so far, okay or not? Yeah. I don't think in your note tells you what does this Jacobi symbol do, right? It just give you a bunch of properties. Okay, I'll try and tell you in the next class what can this do, or at least what's the relation. Okay, but then even before that, I can tell you that when n is prime, meaning the denominator is prime, then this Jacobi symbol is really just the Legendre symbol. Okay, it's just Legendre symbol if n is prime. Okay, because if you split it up, you just get one Legendre symbol. Okay, maybe I'll tell you now. So when n is composite, this equation here has a solution. What implies that a over n, the Legendre symbol of a over n is 1. Only as a solution, this one. Okay. So far people okay with this sentence here? So when n is composite, too many I. Composite. Wait. When n is composite, this has solution, implies that a over n is 1. Okay. So to see this, so this is the Jacobi symbol because n become composite now. So to see this, note that if pi is a prime divisor of n, okay, and if x squared congruent to a mod n has solution, okay, then the congruence x squared congruent to a mod pi will also has a solution. Okay, so meaning if you have solution for the big n, right, for the small pi, you also have a solution. Does this make sense? Does this make sense? So maybe think about some examples. So let's say mod 4. Let's consider mod 4. What thing square to what? 3. Maybe try 3. So 3 square 1. Okay, good. So the claim here is if there is a solution for this, you have also have a solution for, let's say, mod 2. Okay, then, well, 1 is too trivial, is it? You can just take 1. Solution, then. Oh, I think, let me see. Is there another way to see this? Okay, I think I know how to prove this. So let's say we have x squared congruent to a mod n. This implies what? X squared congruent to a plus multiple of n. Right or not? But then this I, right, can divide n. What does this mean? So this means that I can actually rewrite this equation in terms of pi, right? So maybe m times pi. Okay, so in this case here, I can write this congruence as x squared congruence to a mod pi. Okay, so the same solution was solved. Okay, so in this case here, if there's a solution, right? So what does this mean for Legendre symbol? Then first, a of pj will be I. So consequently, if you write down your Jacobi symbol, all of them, all the products will just get you 1. Okay, because all of them will solve it. Because I prove it for any pi. Yes. Oh, oh, sure. Okay. Wait, let me think. Well, I think this statement is always true. I mean, it is always true for this statement, I guess. I guess this part here, you don't need whether n is odd or not. I think so. I think this statement, you don't need to care whether n is odd or not. Yeah, for this part to be true, I don't think you need n to be odd, right? It can be true for any n. Yeah. For this to be whole. It's just that our definition for Jacobi needs, wait, yeah, our definition for Jacobi needs odd positive integer. Yeah. But then for this statement to be true, it can be true in more general setting. Correct? Yeah, because I'm just splitting out this pi from my n. Does it make sense? Okay, okay. Okay, so this is true, but the other direction is not true, you know. So this Jacobi is not as useful as Legendre symbol. Let's see the other direction. So the other direction meaning if the Jacobi symbol is 1, then this has solution. This is false, unfortunately. Okay, so we have a counter example here. So, so unfortunately, it is possible that, so this is the difference between Legendre symbol and Jacobi symbol now. So it is possible that a over n is 1, but there's no solution to x squared congruent to a mod n. You want to think about it for a moment? Yeah, give a counter example. Okay. So you can think of other example, but I'm going to give you a equals to 2 and n equals to 15. So what did you see here? So if you compute the Jacobi symbol, right? So you split into 2 over 3 and 2 over 5. So both of them are not plus or minus 1 mod 8. So you get -1 on both. So you get 1. Okay, good. Then you want to prove that there's no solution. So how do you do? Well, you want to prove there's no solution. Prove there's no solution to x squared congruent to 2 mod 15, right? So this is like an assignment question, right? 2 mod 15. So one way is to use brute force, to try 1 to 14, and then see that it's not equal to 2. But then there's a simpler way, right? You can split your n into relatively prime numbers, right? So that you can use Chinese numerator theorem. So this is equivalently to solve a system of congruence, which is x squared congruence to 2 mod 3 and x squared congruence to 2 mod 5. Okay. So in this case here, how many possibilities you need to check? Here got 2, here got 4, 6. But then if you just check this end, there's 14 of them. So you significantly reduce the cases you need. Okay. And then checking this is relatively easier, right? 1 times 1, 2 times 2, there's no 4. 1 times 1, 2 times 2, 3 times 3, 4 times 4. you won't get 2. Okay? Yeah. Does it make sense? So in this case, you might ask, oh, then what is the use of Jacobi symbol? Okay, so meaning what? If you get the Jacobi symbol equals to 1, you might have a chance to solve it. That's it. Understand? Okay, so to solve it, you need to have at least that Jacobi symbol equals to 1. But having Jacobi symbol equal to 1 doesn't imply that you can solve it. Okay, it just says that it is possible to solve it. Okay, because to solve it, you must at least have the Jacobi symbol. This is a bit like your calculus, huh? I mean, like your first derivative test, right? The stationary point might not be the global maximum. Okay, so this is just one of the criteria that this existence of for the existence of the solution. Okay, it doesn't say that the solution exists, but if it's equal to 1, there's a high chance that the solution. Does it make sense? Okay. Okay. Then shall we maybe not computing this, but sure, we'll tell you what's the property here. So the property of Jacobi symbol is actually quite similar to the Legendre symbol you could type. Yeah. So for example, the first property, as long as you have two numbers that congruent to each other, then their Legendre symbol should be the same. And then you also can split out your Jacobi symbol into products of Jacobi symbol. And then the formula for -1 over n is -1 to the n -1 over 2. Okay, this is the same as the Legendre symbol. And then 2 over n is also the same, n squared over -1 over 8, taking power of -1. Yeah. Okay, so actually, Jacobi symbol work the same as Legendre symbol. But Jacobi symbol will be asking about composite number. Okay, instead of prime. Legendre symbol is asking about prime. But in this case here, I think here A and B, when you split into products, it says that they have to be relatively primes to n. Okay, so previously, do we have this condition? Or we just say that P doesn't divide A and B, is it? Let's see what we had before. I think it's just non-deviant. Yeah, we just say doesn't divide, right? Okay, because it is composite now. Yeah, so maybe it's not enough to say divisibility. Okay, as long as they have GCD greater than 1, then the congruence wouldn't work already. Okay, we don't need divisibility to control, but we use GCD to control. They cannot share the similar common divisor that's greater. Okay. So previously it's the same. Can you recognize that it's the same condition here? Actually, so instead of divisibility, right, we can mention it as a GCD. Wait. Okay, so this condition is similar to saying that GCD of AP and BP is 0. Yeah, it's 1, sorry. Okay. Because P is prime. Okay, so we wouldn't say that P have to divide AB here. No. Because common divisor is a stronger condition. You understand or not? You understand the difference here? So maybe I can give you some examples. So so 4 doesn't divide let's say 10, but the GCD between 4 and 10 is 2. Okay. So at the same time, three doesn't divide 10, and GCD between 3 and 10 is 1. Okay, so here we can see that 4 is not prime, and then 3 is. So when 3 is prime, right, these two condition is equivalent. Okay, if it's not prime, these two condition is not. Yeah, being saying that's GCD of that. Okay. Yeah. Any questions so far? Any question? So here, basically, what am I saying here is divisibility versus GCD. Yeah. So you need to be careful when we talk about divisibility. Are we really care about division, or we just care about common divisor? Okay. So in this case here, you can see that for the Legendre symbol, for Jacobi symbol, we really talk about relative to time, not divisibility. Although we phrase it as a divisibility because it's the same when we talk about prime. Okay, so you could imagine some of the theorem or lemma that we care about. It's not just divisibility, but also common divisor. If they share some common divisor, then something can go wrong. Okay. 11:47. Shall we? Okay. I think it's quite obvious what to do, right? Is it obvious? Or you want to try one of it at least? Is it obvious what to do? Okay, maybe okay. Let's go to orally first. So if you look at A, what would you do in the first encounter? What would you try to do? Who are not relatively prime? 15 and 21 are not relatively prime. Okay, good. So it's 0. Okay, so by definition it's 0. So you don't ask me why it is 0 because we just define it to be 0. Okay. If we define the Legendre symbol to be 0, then this statement here can be implied from there. But otherwise, you just take it as a 0. So this part is 0. Okay. How about the rest? The rest is just -1 and 2, right? Okay. Well, one way is to use the Legendre symbol. Okay, because you know that you can split your Jacobi symbol into product of Legendre symbol, right? Okay, then you go and use your Legendre symbol property. Otherwise, you use this formula. Okay, very similar formula actually. Actually, it's the same. Yeah, actually, it's the same, really. It's the same, really. And then you can prove it. Why is it the same? If got chance, maybe in next class, I will prove it to you. Okay. Yeah. Right, correct or not? N-1/2 is the what's that? Euler criterion. Euler criterion. P-1/2. Can you still remember what's the name? Yeah. Euler criterion, right? Yeah, P-1/2. But then, yeah. So we are safe to remove mod P here. Do you know why? Because your A is just -1. So this thing will jump between 1 and -1. So your mod P can be removed, safely removed. Okay, but then this one, there's no mod P anymore, but then we replace this power with n squared -1/8. But then these are just coming from the fact that we know that Legendre symbol work this way, and then Jacobi symbol is just like product of them. Yeah, this is the moral. If got chance, maybe I can show you next time. We'll see how. Okay, so far, are you okay with this properties here? Okay, so the moral here is Jacobi symbol have the same property as the Legendre. Just that when Jacobi is equal to 1, it doesn't always tell you that the quadratic congruence has a solution. It might not have a solution, which I showed you just now. But at least it got the chance to get a solution. Okay. Okay. How about we break again until 12:01?哎，没有签到，两个是，
我们只有平行移。
这个，
对，
还有
我
啊，对不起啊，
那边呢9点然后去2点，7点和8点一起来，也是大型队嘛。我想要发达的改变，我是实话跟我说。最后用了200几个礼拜，一桶球，这2个就有关系方便。我买我用买个Seng，我这个用把石头跟了。快点两到3个，快点用完了，没有了，大便过去了。
哎，
说的，
你是谁？维权？
那就
诶，我点了你，
我刚
我刚才没有叫到你名字嘛？
我刚没在。
哦，OK，可能我看漏了。OK，维权点了。
好
Yes，
我问题是为什么这里是A和B？这是怎么来的？
怎么得来啊？想想啊，因为我想想，
我问了人家也没有什么得到答案。
诶， 其实如果我看看，OK，他要考虑这个 a over 2的点，他只是为了考虑1到这个位置，你可以选，a over，其实你可以选 a over，给我讲一下啊，你可以选 a over，你可以 OK，说这个号码不是，你不一定要选 a over 2，你只要选一个号码大于 a 减1 over 2就可以，但是又不可以去到 a，又不可以去到下一个是什么？加一过后是什么？加一过后是
就是 a 加一 over，
a 减1 over 2加1什么？
就是 a plus one over
啊，你不可以去到，我可以换吗？
可以
呀，你不要选一个号码超过 a 加1 over 2就可以了。
是不是就是因为它是congruence，是说就是它那个就是 a 那个数的一半，就是它那个整数
其实是这个 lemma，这个 lemma，这个你要知道是这个，为什么这一个只需要算到这个？可是算到这个过后，你这里的这个四方形只要选的是包含这个的 lattice point 就好了。呀，你可以选这两个值之间的一个号码都可以，不一定要 L
大概明白。
呀，重点是这一个比较重要，就是为什么你只要数到 P 减1 的话，这一个会比较重要。这一个过后，等这个四方形只是在考虑这些点。
然后这个是就是 t，然后它那个括号里面是 a 逗号什么东西，然后这是 b 逗号什么，
对，反方向，一个是另外一个反方向。
就是这个是t a 逗 b，
呀，这个是 TA 逗 B，
然后这个是
TB
b
逗
的，就它也是那个固定的一个。
不定，不定。
好的，谢谢。
OK，哎，看下这个，你的名字啊，我帮你点了。
我之前有一节课我没听到，我上厕所去有一节课想起来，但是可能已经对，这个是对
没有，
这个意思
这是你吗？这不是你，
啊，那对
这不是你。对，
是我另外一个课，然后他就是我收到一个邮件，他说我前2个周出席率是67%，但是我每节课都去，然后可能是我忘记去签到了。那我觉得就是您作为老师，就是作为一个学生，就是跟那个老师发邮件，就是请求老师帮我把那个层面都给发签到，然后再反馈给我的学术条件的话，我应该怎么发邮件？
你只要 forward 那个，你 forward 那个你的那个 你的那个 email，告诉他说我几次有来哦，然后可能他会让你证明你这样有来的，你就要去跟他聊啊什么之类的。对，就这样。
就是一般这样老师也会同意。
哦，然后你就 CC 你的那个 academy让他知道你跟他的聊天啊，就是这样。OK，呀，我不懂那老师要怎么去证明你的人，可是你就是要跟他说你其实有来，
对呀，
然后你 CC 你的那个 academy affair 的那个 coordinator，
就是我这个专业的。
对，然后他就会看哦，到底发生什么事情。
哦，
哎，
然后他那个就是我那个出席率，如果是不到100%的话，就是如果是在那个80到100之间，会影响我的最终成绩吗？
成绩是不会影响啊，但是之前我们是会来 ban 你去考试啊，就是你不能考试，其实
就是以前有这样的例子，
有，
就是出席不到80就不让
对，不会影响考，怎么说呢？不会乱扣你分，但是你连考试都不可以这样子。
但
如果你考试都不能的话，就是哈，连那个我就不懂怎么做啊。
但是我还是得跟那个老师
肯定要
说一下。
呀。
好的，谢谢。
OK，双峰、心灵、李心凌，OK，嘉凯，Yeah。 唢呐 ，OK， 家福，陈家福，陈家福这样的，冲铺汪冲铺，汪冲铺，不易，谢谢，崔文倩，唱序，Yeah， 宋浪空，小佳怡，赵泽宇，T 收视，T 收视，OK。首席 and then 陈少航、陈卓、李乐山、彭奕晨、赵星辰、诺、玉涵、彭玉涵呀、彭玉兴、Sardine、Sleeping。Okay, let's continue. Okay, so the next thing is what do you expect next? What's the after property of the Legendre symbol? What do you learn? Recall. After property of the Legendre symbol, what do you learn last time? Do you remember? What's the last thing we spent a lot of time? Legendre symbol. We just do revision in the first hour, right? Law of quadratic reciprocity. Yes. So we want to ask whether this law work for Jacobi symbol or not. Okay. So what do you think? Yes or no? If the answer is yes, okay. Luckily it's yes. Okay. So it's the same formula. Okay. So we also have the law of quadratic reciprocity for Jacobi symbol. Yeah. Then I think we just left this for exercise. Is it okay? Yeah. So maybe one thing to remind you is this Mn here have to be relative prime odd positive. Previously, your Mn are odd prime, right? Okay, but in this case, it's relatively prime is enough. So this is the really the difference between Jacobi symbol and the Legendre symbol. Okay, Legendre symbol you ask for odd prime. Jacobi symbol you ask for relatively odd prime odd number, relatively prime odd integer. Okay, you cannot simply put the adjective odd prime, relatively prime odd. Okay, it's different. So prime number is something that has divisor 1 at itself, right? Relatively prime just means that the two things has GCD 1. That's it. Okay, yeah. It could has a lot of divisor, but then they cannot share the same divisor other than one. Yeah. So far, any question? Any questions so far? Okay, so maybe you need to be a bit careful. Okay, if no question, then we will start new stuff today, which is continued fraction. I want to have a head out warning to you. This chapter is quite tedious. So careful. It's very kind of tedious. So let's start. So meaning when we go to chapter 6, chapter 7 is not far already, so meaning we are going to end this course soon, very soon, pretty soon. Yeah. Okay, so continue fraction. So what do you think about continued fraction? You learn fraction, right? 2 over 3, 5 over 6. But continue fraction means what? You can continue to write fraction inside a fraction. Okay, so there's a fraction inside fraction. Okay, I mean, is it hard to imagine a fraction inside fraction? I think maybe you can think of something like that. But then this is actually a fraction, right? You can simplify it like that, right? And then, okay. But then in this chapter, we not need to deal with this finitely many fraction inside fraction. We will write like really infinite of them, something like that. Repeat the pattern. Can you imagine? Yeah. Okay, so we have a fraction inside fraction. Okay, so how do we do this? So first of all, let us introduce decimal expansion. Actually, we mentioned this a lot of time, right? Decimal expansion, but really now we only tell you the definition. So any real number x can be written in the form of the following. So x equals to the floor of x. So this is the largest integer. So remember last time, I mean like just previous hour, we told you that x minus the floor, the value will lie in between 0 and 1. Okay, so we can write it as a sum of fraction such that this CJ is over the power of 10. Make sense? Does this make sense? So maybe I can write some number here. Let's say 2.13. 2.13 is what? 2 plus 1 over 10 plus 3 over 100. Like that. Okay. Good. All right. So then this is called the decimal expansion of x. So in general, how do you compute this CI? In general, how do you compute? What do you think? How do you compute this CI? Okay, so maybe I use the same example to tell you. So for example, so well the floor, you let's say assume that you can get the floor, and then you get 0.13. Okay, so the question now is how to get C1 equals to 1. Let's say you only know how to take floor. You can multiply by 10 on both sides. Right. You can multiply by 10 on both sides, such that you push the 1 up, right, up to the integer place. Okay, so that you get 1.3. Then the floor of this is exactly 1. So this is the C1. Can you imagine how to get the next one? Do the same game. Okay, so you do the same game. So you just set so let's see what's the next game. So you set y0 to be x, and then you computed your C1 already. Okay, so let me write down this process. I think we have to get this process right. So we will let C0 to be the floor of x, and then how to get y1, gamma 1. So wait, let me see. So let this to be this, and then we will find C1 to be the floor of gamma 1. But what is the floor of gamma 1? The floor of gamma 1 is actually 10 times the gamma 0 minus C0. But then what is gamma 0? So at the same time, we need to set our gamma 0 to be, this is a bit like your coding or induction. So y0, we also set it as, actually y0, we set it as x. Okay. So then So then actually we need to find y1 first. So here actually it's better that we write, we know what is yi first. So shall we put here? Yeah, where? Okay, so what did you see here? Okay, what we see here is Ci is the flow of this thing, okay, which we call gamma 1. Okay, we need to call it a name so that we don't need to specify this every time. But then what is this? This is exactly using the x minus the flow of x, okay, x minus flow of x, and then times 10 because you want to push the next decimal up. Okay, push it up so that you can get the number 1 there. Okay, does it make sense? Okay, but then how to get the next one? How to get the 3? How to get the 3? How to push it up? Okay, so if you look at this algorithm carefully, so what is C2? C2 is on gamma 2. But what is gamma 2? So gamma 2 formula is what? So 10 times gamma 1 minus C1. Okay. But then what is gamma 1? So yeah. Okay. So gamma 1 is just 0.13, right? Okay, in this case here. And then you take away C1. Okay. So let me check. So what is gamma? Sorry. Gamma 1 is not 10, not 0.13, but then it's 10 times 0.13. Okay, so the whole thing inside here is gamma 1 actually. Okay, so can you realize that in gamma 1, there's no flow of x anymore? There's no C0 anymore. Can you see in the gamma 1? Okay, so you repeat the same game. So treat the gamma 1 as the x again. Okay, take the gamma 1, take away the flow of gamma 1, and then multiply by 10 again, shift 1 up again, and then take the flow. Okay, then you do the same game. Okay, so you go to the next one, then take a different shift again, to the next one, shift 1 by 1 again. Does it make sense? Okay, if not, I suggest you to try a longer example. Maybe you go back and try like 2.1314 like that. Okay, try this method. Okay, does it make sense so far? Any question? Feel free to ask. I was like asking my FYP, right, or my master. If you don't have nothing to present, you don't need to come and see me. I don't want to hear like, oh, I read this. There's no use for research like that. You have to ask question actually. Okay, question is more important than what you know, because what you know, it might not be what you know. But what you don't know is really what you don't know. That is true. And then you actually learn from what you don't know. You don't learn from what you know. You understand? So you have to bring a lot of questions to class, to anything, discussion. Okay. Because I have a case that the student was very good in the final can get 100 assignment. And then turns out that he or she cannot finish FYP, she cannot do research. You understand or not? So you just write down some answer that you think is right, that the teacher think is right, but you don't know what is. You understand or not? This is possible, and then this is very common also. You just write down some answer that the teacher like, without knowing what are you writing down. You understand? So this is a very serious issue. Okay, if you really want to study or do research or whatever. Okay, so please know what you are doing. Okay. Yes. So that's it for this part here. That's it for this part. Okay, how about we do some exercise? Okay, do this exercise. Try and find the decimal expansion of this. Okay, how about I do one first and then you do one? Okay. So let's do A. Yeah, let's do A. So we will use the same game to do here. So let's first fix gamma naught first. Okay, well, I mean, we start with the number that is given. So what do you think? What's the floor of a gamma naught? 0, right? Because this is something less than 1, so it is 0. Okay. So imagine you don't have calculator in your hand now. Okay, so you're going to use this method to find it. Okay. So what's gamma 1 then? Okay, so gamma 1 is like pushing up, right? Take the difference and then push up one spot. So what's the difference you are doing here? So you take the original number, take away the floor. Okay, this thing would be positive, and then you shift it up by 10. Okay, you shift out by 10, and then what do you get? You get 70 over 16. Okay, and then what is C again? So remember, all the C is just taking floor of gamma I. Ci is just taking floor gamma I. So what's the floor here? The floor here is 4. Okay, so I'll go to the next one. Again, you take the difference between gamma 1 and X floor, and then shift up by 1. Okay, so calculate it. So you take gamma 1, take away X floor, and then shift up by 1, you get 16 over 60. Sorry, 60 over 16. And then C2, you will take the floor of this thing. Okay, 3. And then gamma 3 again, you take the new gamma, take away X floor, and then shift up by 1. Okay, and then C3 will be 7. Okay. Do you think we will stop one day? Yeah? You sure? You're pretty sure? Depends. Okay, obviously depends, but for this case, you think we'll stop or not? Yes. You so sure? Uh-huh. Okay, finally, I think we need to stop here. So finally, we can stop at gamma 5 because you will get 0 there, and then the floor of 0 is a 0. So altogether, what do we get? You can use your calculator and check, or use the division algorithm. This one is 0.437. Okay. So this is a very primitive method to find this decimal expansion. Otherwise, if you use division algorithm, what would you do? You would like divide 16 by, let's say, like 1, 2, 3, 4, right? Like 7,000 like that. And then you get 4375 like that. Carry on now. Okay, yeah. Okay, how about you do the next one? Okay, I give you 3 minutes to try this one. See what you get. 37 over 14. Okay, try and practice this inductive way to find decimal. Does this number end? Huh? Does this number end? Never end. Seriously? I'm gonna calculate until you cry. Hmm? 37 over 20. Oh yeah, never end. Yeah. Okay. Maybe you can stop somewhere. It never ends. Yeah. So maybe it's like 6.24258.7 blah 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 blah. Okay. Yeah. Okay. So yeah. Okay. So how about the other way? Can we convert number back to fraction or not? Okay. So for the repeated one, we can. Like for the rational, we can't, right? I think we mentioned it before. Okay, so what's the technique here? Well, let's show you the technique. I think you can very easily get hands-on. So what happened here was you see that it has repeating 3, 9. Okay, so the notation for repeating is dot dot. Okay, if we put a dot dot there, meaning these two things were occurring again and again. Put a dot on the numbers, depending whether it's a 1 dot, 2 dot, or 3 dots, or multiple dots. Okay. So what to do is you get a string of things that repeat itself. Okay. So if you take 100x, right, you get 839 over 39393939 again. Okay, so which is just 839 comma 39 dot dot. So in this case here, if you take 100x minus x, what you see is what you will see is the string of repeating decimal, right, will disappear. Okay, after the decimal place, such that you just get a integer. Okay, so this is what you want in your fraction, because inside a fraction you only have integer. Okay, you don't have decimal anymore. Okay, so in this case here, you can see that this trick here actually really give you 831 over 99, which is 277 over 33. Okay, so actually you can try and check whether this is true or not. Okay, you want to try the next one? You want to try the next one yourself? Yeah, try the next one. What can you do to remove the string of repeating numbers so that you get some integer? Yeah, try B. I give you 3 minutes. You try B. any way to remove the string of repeating? Sorry? Huh? Make a series? What do you mean? Geometry series. Geometry series for the so 2.2, or you can write it down the fraction form. Yeah. Also works. Yeah. I think one of the way you see this is like the geometry series, right? Yeah, you can use that. Otherwise, you can try something like this. So let x to be at 0.213.09, right? Okay. So I guess this 2 dot will implies that anything in between it will repeat again. Okay, so this is the notation. Then 100x will make it a repeating string behind the decimal place. And a similar trick like before, we push one of the part of the repeating pattern out and then keep the 309 like that. So in this case here, if you take the difference, I can remove the repeating string again. Okay, in this case, I get 2820488. Okay, so from here, I'll get 820,488 over 999,000. Okay, so if you simplified it, you'll get like 68374 over 8325 like that. Yeah. Uh, one more 0. Oh yeah, thank you. Okay. So this one, like that. Is it enough? Okay. Okay, makes sense. Okay, so you try to make 2 string of repeating pattern that can be cancelled, but then their difference is some integer. Okay, and then you can cook up this fraction. Okay, any questions so far? Okay, so we're trying to make the repeating pattern occur at the decimal after the decimal place, and then we remove it by taking difference. Okay, so next part is we said that the decimal expansion of a real number is finite or periodic if only if x is rational number. So actually this is a theorem, but at the start of the class I told you that rational number is something that you can write it as a fraction, right? Okay, so actually this is a theorem. Okay, you can prove it with the tool that we have learned now. Okay, yeah. So should I tell you what terminates means? Terminate just means that if you consider the CI, right, the CI will be 0 for large I. Okay, so it will stop. What does it mean by periodic? So you could have the dot dot appearing in your decimal expansion. So what's the way to write it? So here it is. So a decimal expansion is set to terminate if there exists a positive n such that for Cn and then every n larger than it, Cn plus 1, Cn plus 2, it will stop. There's nothing anymore. For periodic set, there exists a positive n and a k such that Cn plus k equals to n. So meaning a chunk of k things will repeat. A chunk of k things will repeat. Okay, so k is like shifting. Okay, ck is c0 plus k is equal to c0. If c1 plus k is equal to c1, so shifting. Okay, shift by k. Okay, so this is actually a theorem to prove here. And this theorem actually is quite tedious to prove it. So if you see the notes, it's almost like 3 pages long. It's not hard, but then you need to argue a bit. Okay. Otherwise, everyone happy with this? Again, if you have a rational number, then the decimal expansion is finite or periodic. Okay. Next, this one is more interesting actually. Although the phrases here, I mean the result actually not surprising, but the phrase is interesting actually. The decimal expansion of the real number is finite if and only if x can be written in the form of r over x, where all the factor of x is divisible by either 2 or 5. Okay, so this says that if your decimal expansions terminate, then this x can be written using denominator such that the factors is divisible by 2 or 5. Okay, why 2 and 5? 10, right? Because in the decimal expansion, you are dividing by the power of 10. Yeah, so this is one way to think about it. Actually, yeah, it's the only way to think about it. Okay, yeah, that's why this 2 and 5 appear because of the 10. 10, 100, 1,000, 10,000. Okay, so far, so good. Shall we? Do you want to see the proof of this? Can? Okay. I think this proof is pretty intuitive. This proof is kind of intuitive. So suppose the decimal expansion is finite first. Okay, so what does this mean? This just means that for large n, Cn will stop, right? For the rest, it will be 0. Yeah, this not doing great. Okay, then x can be written as the floor dot C1 up to some n. Okay, stop somewhere. But then what does this mean? This just means that I can rewrite this whole thing as this, okay, over 10 to the n. Right enough. And from here, if you just do simplification, what sort of simplification? What are the factors here? 2 and 5 only. So even if you do simplification, you can only cancel out 2 or 5, but you still left with 4 or 5 factors. Yeah. Make sense? Okay. Yeah. Okay, so this is part of it. So even if we do simplification, so this is one direction. If we simplify the fraction, x, the resulting denominator still only contain prime factors 2 or 5. Okay. How about the other direction? Okay, let's look at the other direction. So the other direction is more interesting. Okay, so suppose that you have a rational number such that the denominator is in the power of 2 or 5. Okay. So meaning your x will look something like 2 to the a times 5 to the b. Okay, for some maybe. Okay. So how to prove that some decimal expansion is finite? So well, I mean to look for decimal expansion, we want to write it as a sum of ci over the power of 10, like that. Okay, so that's what we wanted to do. So how do we do that? Well, then what's our x? Our x is equals to r over 2a times 5b. Okay. But then how do we write it as a power of 10? Power of 10. How is it possible to write it as a power of 10? I mean, maybe I give you something to think about. Let's say if I have a 2, right? If I have a 1 over 2, can I make it a power of 10 at the bottom? How? I'm sure you know. Huh? Multiply by 5, right? Okay, so you can multiply top and bottom by 5, like that. Right. So let's say then you can see that these two actually represent the same number, right? 0.5. But then let's say I have like 2 times 5 to the square. Okay, can I write it as a power of 10 or not? Times 2, right? So what are you doing really? What are you really doing? You are like filling out the power. Filling out the power such that they have the equal exponent. Okay. So what we will do is we multiply top and bottom by 2 of maximum of AB minus A times 5 to the max of AB minus B over 2A times 5B. Okay, times 2 to the max of AB minus A times 5 to the max of AB minus B. Can you see what am I doing here? So I'm trying to figure out how many things I need to fill up, and then I just fill enough of them. Okay, I see which one is larger. Okay, and then I fill that many. That makes sense? Okay. So in this case here, we already write it as what? R times 2 to the max of AB minus A times 5 to the max of AB minus B over 10 to the power of maximum of AB. Does it make sense? Okay. So from here, can you see that this is already a finite decimal expression? Yeah. Or should I show you this? Your finite decimal expression. And you divide by some power of 2. Okay, because this power of 10 is finite, so it's a finite decimal. Okay. Okay, so far so good. So far so good. Do you want to continue or should we stop here? Stop. I think we should stop here. Yeah, that's part is the new stuff. Okay, in that case, we'll see you on Wednesday. I'll see you on Wednesday. I'll update you whether Friday is a holiday or not. Hello 啊，点啊？你们在哪里啊？我刚放学，你们在哪里？